Hi everyone. So today we are again going to discuss electrochemical measurement method for corrosion analysis. And if you remember our previous discussion, we have already talked like electrochemical corrosion measurement can be divided into two categories. The first one is based on the application of DC currents. So when we are applying a DC current and measuring a voltage, so this is the one method. Then second one is if we apply the AC current and then we measure the voltage. So if you remember in DC current, we can have three different type of procedure. One is linear polarization technique. Second one is open circuit potential versus time measurement. And the third one is Tafel extrapolation method. So recently we have discussed the Tafel extrapolation method. And today again I would like to continue from the previous discussion in this regard. So we have already updated about these three variety of methods. Today let's say how we are doing these methods in laboratory as well as how we can use electrochemical polarization methods to monitor or to analyze the corrosion in field also. So if you remember, we have already discussed about electrochemical cell. So in laboratory, we are just having a simple electrochemical cell in which there are three electrodes. One is counter, one electrode is reference, and one is your working electrode or the metal on which how the corrosion is going to affect that metal or what is the corrosion rate of that metal. We are going to analyze that. We can say it's an anode. So typically then we can also have some kind of gas inlet outlet so that there should not be oxidation of any species or if any oxygen is present there. So because we are going to measure the electrochemical current or electrochemical voltage and we are expecting these things are coming due to the corrosion, but if anything else is there then of course this is going to interfere in the result and then our estimated corrosion rate or the estimated corrosion current will not be accurate. So therefore some other protocol or we can say the set of measures are required. So therefore you can see here a kind of typical corrosion cell where we are having gas outlet, gas inlet to have the inert system here. Then you can see the auxiliary electrode here. Similarly, the working electrode is here on which we are going to observe the corrosion, and then the salt bridge connection and then reference electrode with salt bridge. But ideally if we draw a typical diagram, it will look like this. Let's say we have a potential state by which we are able to apply a defined value of current and we are able to measure the change in voltage or potential. So the system is something like that. Our working electrode, if you can see my cursor, and our auxiliary electrode, both are connected or both are having in one cell, and then by the salt bridge probe we are having another half cell or you can say just a reference cell where we are having another reference electrode, and here they are mentioning it saturated calomel electrode. So either we call say a counter electrode or auxiliary electrode, and another is the working electrode. Both are in the same polarization cell, so we are calling it a polarization cell, and in other half we are having a reference cell. So with respect to this reference cell we are measuring the potential of a working electrode and the potential of the counter or auxiliary electrode, right? So in laboratory, as I told, we are having the working electrode, which is primarily electrode whom corrosion rate is being measured. Counter electrode or auxiliary electrode, this is kind of inert electrode material and generally made of graphite or platinum. Reference electrode, which is basically having a reproducible potential, and with reference to this electrode we are measuring the potential of counter and as well as potential of the working electrode. Electrolyte, so this is also very important. So electrolyte, high resistive produce not so good effect. If it's very high resistive, then it is already going to contribute to the solution resistance. Then whatever polarization resistance we are measuring may not be accurate because the value of corrosion resistance will be added there. So therefore we require a conductive or highly conductive electrolyte. So these three setups are required, or the things are required when we are doing the corrosion analysis using polarization method in laboratory. Similarly, what kind of things are done when we are using electrochemical method, particularly polarization method for doing corrosion analysis in field? So polarization resistance method is most widely used in the field because this is more easier way. Moreover, this is also not so dangerous as compared to the other like extrapolation method or other way. So we are going to measure the polarization resistance, and based on the polarization resistance we generally calculate the corrosion rate. So here providing corrosion rate measurement within minute means the measurement setup is very fast, very quick, and it does not affect the ongoing corrosion rate. Means here we are going to apply very small amount of current which is producing the polarization, so it is not going to give any adverse effect on the existing corrosion rate. So material is not going to degrade due to the corrosion measurement. This is a kind of least effective method which is not going to impact anything on the material corrosion behavior. So if we compare the two parameters, or the parameters, what are the differences when we are talking about the experiment at the laboratory, or when we are talking about the set of parameters when we are doing the measurement at the field. So let's say if we are talking about the auxiliary electrode, means the counter electrode. So as I told you, if we are doing this experiment in the laboratory, then of course the platinum or the graphite are the common choice. But this is not applicable in case of field testing. There generally the same material, whatever our working electrode material, the same material is used as a auxiliary or counter electrode. Then the next point is reference electrode. So if you see in the laboratory, generally we require a standard reference electrode such as saturated calomel electrode or AgCl electrode or many others. But in laboratory again, reference electrode is also the same and the same material which is the counter electrode and which are the working electrode. So normally made of the same material as of the working electrode. So counter, working and auxiliary, all three electrodes are made using same material in case of field testing. The next is Tafel constant. So Tafel constant, you know, it's very the constant which are basically used to calculate the corrosion rate if we are having the value of corrosion resistance So by doing this measurement, we can calculate the corrosion resistance or polarization resistance, I would say. So using polarization resistance, but we also need the value of Tafel constant. So in case of laboratory, we have the freedom to do the Tafel extrapolation method and can calculate the Tafel constant. But in Tafel measurement, we need to apply a high voltage. This is not so safe and it may induce further corrosion in the system. Therefore, when we are talking about the field testing, we are not doing the Tafel measurement. We are not measuring our own Tafel constant. We basically use the normalized values or the standard values available in the literature for a particular material or a condition, right? So here again we are using a normalized value for Tafel constant. Again, capillaries used there, we don't use any capillaries or we are not making any kind of you say salt bridge. Corrosion potential. In case of laboratory measurement, of course, we do measure the corrosion potential and we report this corrosion potential with respect to the standard reference electrode. But here we just measure only stable values or stable values are noted because the conditions are different. So these are the basic difference if you are comparing the laboratories measurement techniques and if you are comparing what we are doing in the field testing. Okay, so all three electrodes are the same material. Tafel constants are normalized one or the standard one, and as well as corrosion potential also we just take a standard values or only stable values we noted, not all the values, we didn't go in detail. So these kind of setup can be deployed in the field if we are interested to utilize the polarization resistance measurement based method to analyze the corrosion. So if you see the figure A basically demonstrates a typical 3-electrode polarization resistance probe. So I would not say it's an electrochemical cell, it's a probe where we are having a 3-electrode, namely counter, reference and working. All are made by same material. And you can see here the cross sectional, it look like, so this is the one electrode, should say, the second one, and then this is the third one, and this is the image of this cross sectional. Means your one electrode here, another electrode here, and then the third electrode is here. Now this is the setup, and this setup can be deployed in different way. So here few examples are there at figure B, C and D. So B means how we can install this in pipe fitting. So basically you can see these are the pipe fitting, and this is similarly this 3 probe. This is installed here in a pipe fitting. In the C, in the well line, again just this pipe fitting overlap, this simple pipe or well fitting. This is the pure probe. The D is the in pipe T. Let's say the T junction is there in the pipe, then somewhere T junction we can fit in the pipe. These are the typical example, like how we are going to fit the probe to measure the corrosion. So once we want to measure, we just fit this probe, and later on anytime we can monitor or we can measure the corrosion resistance, and based on the corrosion resistance and other parameters we can calculate the rate of corrosion. So these were at least how we are doing corrosion measurement in laboratory, how we are doing the corrosion measurement in field. Now when we are focusing about the polarization based methods, whether it's resistance based, even any other two like OCP versus time or Tafel extrapolation, there are few limitations, or we can say there are few things we need to be very careful when we are measuring. Otherwise the data or whatever calculation we are doing, that may not be accurate. So I'm just going to pinpoint few things which are very important if we are trying to determine the corrosion rate. So first of all is solution resistance. Let's say we are not focusing about the field, because field is more generic case, or the we are many things we are just considering standard, so not very accurate data we are going to get, but at least in the laboratory scale we are having more focus or accurate data. So if we are thinking about that perspective, then I'm talking the first point, that is the solution resistance or the resistance of the electrolyte. So let's say you are connecting this counter electrode with the working electrode, and we are measuring the current, and based on that measuring current we are estimating the polarization resistance. But remember, if we are having a high resistance of the solution itself, then we are going to get the resistance of corrosion as well as we are going to get the resistance of the polarization. So the overall resistance will be added up, means the resistance of the solution as well as the resistance of the polarization. So whatever resistance we are measuring, we are thinking this is the resistance of the corrosion or due to the corrosion, but actually this is having two components. One is the resistance of the electrode and the second one is the resistance of the polarized device or polarization resistance. So we are doing something wrong here. So it is assumed that RAS, the solution resistance, is low, means highly conducting solution, so that measured RS is equivalent to the RP. So whenever we are doing experiment, our electrolyte should be very conductive. The resistance of the device itself, or the resistance between the counter and reference electrode, should be very less, or at least as compared to the RP it should be very less, so that whatever measure resistance is there can be considered equivalent to the polarized resistance, right? So this is one limitations or one thing that we need to care when we are doing the corrosion rate analysis at laboratory. So if the RS value is appreciably, then measured corrosion rate will be underestimated. Higher value of RS exhibit a higher value of R, and then we are calculating the different value of corrosion rate, what it is not actual. So the error due to the RS in the RP component is normally significant in the system with high corrosion rate and low conductivity. Now the second paragraph is scan rate. Scan rate means how slow or fast we are switching the applied current. So see, if we are talking about corrosion current measurement, so basically that is governed by the Faraday law. So corrosion process is known as the Faraday current, and then the relationship between the measured current, capacitive current and the Faraday current can be written as this formula that is well known, like I total is equivalent to the Faraday current plus capacitive current C dV by dt. So here this point dV by dt is also contributing over I total. So dV by dt is the scan rate, change in the voltage if you are changing the voltage, or vice versa if you are changing the current. So as a result of this error, the corrosion rate is overestimated. Then minimize the error due to the capacitance current polarization estimate are conducted at lower scan rate, right? So the scan rate is also an important factor, and we should be very careful while choosing the scan rate during the measurement. Otherwise, it is also going to contribute in the inaccuracy, or it will also create inaccuracy in the corrosion rate estimation. Now see about the next point, that is electrode bridging. Means we are having electrode separated, right? But if somehow one electrode is corroded, and some kind of corrosion product. Let's say the iron is there, so iron oxide is created with the corrosion, that's rust, and this rust is so much, it is having a kind of some kind of internal connection with the counter electrode. So now these two electrodes are making a bridge through the corrosion product. So what is happening? We are expecting a corrosion current due to the electrochemical cell, but actually what we are getting, that is the product of corrosion reaction electrically connected the electrode. So basically when this is electrically connected, so we are not getting actual current, right? So this is another one problem. So this usually happens when the conductivity of the corrosion product are higher. So maybe some corrosion product are highly conductive, otherwise if they are less conductive, then of course the conduction will be through the electrolyte, not through the conducting. But we don't know what kind of corrosion product is there. So this is one possibility. So we should think about this possibility. There should not be a formation of electrode bridge or electrode bridging. This system we have as an electrical circuit rather than an electrochemical corrosion system, and when this problem is suspected, the distance between the electrodes should be increased. So you just separate out these two electrodes and increase the spacing between these two, and by this way we can reduce the effect of electrode bridging. Another parameter or another factor which can lead to the difference in the estimation of the corrosion rate, the presence of oxidation reduction species, means we are expecting this reaction is happening due to the corrosion of metal, but let's say in your cell, if some oxidative species are there, so maybe your cell is having the oxidation reaction, and due to this oxidation reaction we are generating the current and we are measuring the change in the voltage or change in the current. So that is not accurate measurement of the corrosion reaction. Similarly, if there is any reductive species are there and they are going to reduce at the electrode, then whatever current we are observing, that is not accurate current. So if electrochemically active species are present in the electrolyte, they prefer to undergo a reaction rather than a corrosion reaction. So our estimate will be different. Other parameter is variation of the corrosion potential. Means when we started our experiment at the beginning, we just measured the open circuit potential, that is also known as the corrosion potential. But if it is fluctuating or if this is not fixed, then whatever current we are measuring or whatever resistance we are calculating due to this current measurement, that will be not accurate. So we are not getting a meaningful result. So if the corrosion potential does not stabilize, then electrochemical technique may not be used. So if your material is giving a stable corrosion potential, then only that material can be tested using electrochemical technique. Otherwise, we should not prefer to use electrochemical technique in the corrosion analysis. Next, diffusion control condition. Means we are expecting the reaction is happening due to the reaction of basically the corrosion of electrode, but sometimes it is happening at the cathode side. We are having some ions, so it's a kind of equilibrium conditions, and now due to the corrosion we are observing the current. But if some species are there, or we are having a very quick charge transfer and it is very high, so at the cathode side we are getting large number of ions which can be reduced, and we are forming a depletion region. Then what will happen? This depletion region means your cathode is not enough to reduce all the ions at a time, and it's formed some kind of a layer. So whatever actual corrosion current is there, that we are not able to observe because this layer is there and that is creating a kind of barrier. So if your process is diffusion control, At this stage, the reaction rate is controlled by the rate of diffusion of the species, because the species is going to diffuse and then it is going to reach in the cathode. So diffusion control corrosion, under this condition the results of the corrosion method are not accurate. So these were the few points. One more is, we are thinking everything is going on perfect, all corrosion is happening a kind of uniform corrosion, and the things are considered very ideal. But there may be a case when we are having a localized corrosion, the formation of pit, the formation of some kind of cracks. So if that is the situation, then this pit or the crack, they are basically going to give the difference in the corrosion rate. The current or the reaction, whatever happening at the electrode, will be different. But we are thinking this is the localized, it's a generic corrosion or the uniform corrosion. Then our estimate is different, whatever as actual. So it also alters the electrode geometry as well as the surface area if the corrosion is not generalized, and all of which result is a change in polarization response, which is difficult to quantify. So means it's very difficult to quantify the localized corrosion or any kind of specific corrosion by doing this polarization method. So these points we need to be considered while we are monitoring the corrosion rate using electrochemical technique. So that was the few things whatever we have considered during the electrochemical measurement. Now in the same domain, let's think about the current, where we are having the AC current and we are applying an AC current and we are measuring the change in the voltage, or how we are going to measure it. So the technique is well known and its name is electrochemical impedance spectroscopy. So rather than calling it a resistance, since this is the AC current, we are going to call it impedance, right? So now let's see what is here. So what do we mean by the impedance? So here we are basically going to use the AC excitation and to monitor the corrosion conditions or to analyze the corrosion, and we are going to apply different frequencies which may range from few megahertz to few kilohertz, right, depending upon the materials. So the current voltage is measured when a small amplitude of voltage or current is applied to the working electrode. So although we are applying AC current, but within that AC we just select a very small component of voltage or a current and we just apply this with varying frequency, and then we measure few parameters. So in AC excitations, if we are talking about the Ohm's law, or like how the resistance is going to be changed, so we can say this is not the resistance, this is the impedance, and that can be written as V, the potential, is equals to the current I multiplied by Z. So Z is the impedance. So basically V is equals to I Z, rather than writing V is equals to I R. So R is replaced by Z and Z is known as the impedance. So Z is the impedance and represent the AC equivalent of the resistance. So in case of DC circuit, so resistance is equivalent to resistance, and in AC circuit this is known as the impedance. So both are impedance and resistance are the similar nature, only the difference when we are having DC or AC inputs. And the magnitude of impedance Z can be given as same, the change in the voltage with respect to change in the current. So Z is equals to delta V by delta I. So frequency dependent impedance. So here because we are changing the frequency, so we can write Z omega. Basically how the impedance is going to be changed with respect to the omega, because we are also measuring with respect to change in the frequency. We are applying a low frequency to the high frequency range. So we can simply write Vt by It, and where basically the change in the voltage with respect to time and change in the current with respect to the time. So it's frequency dependent, where you can say It can be written as I0, the maximum amplitude of the current, sine omega t plus theta. So omega is the frequency by which we are having the AC signal, right? T at the time at which we are measuring the total current or the applied current. Theta is the difference between V and T, the phase difference between the signal of voltage and current. So Vt can be defined as the voltage at particular time t, can be defined as the maximum value of voltage V0 and sine omega t, right? So by if we use this value It/Vt, then we can define the frequency dependent impedance. So value is already I told you. It is the instantaneous current, omega is the angular frequency in radian per second, I0 is the maximum current amplitude, theta is the phase shift in radians between Vt and It. See here. So if you have Vt like this continuous line, so It could be like this. When Vt is 0, it's just a representation. It could be possible that current is 0, because this is the AC signal. So you don't know. When the voltage is 0, the current could be maximum. While when the voltage is maximum, see the point here, the current could be 0, right? So basically there is a shift. You can say there is shift of how much? Here it's almost opposite, right? When voltage is maximum, current is minimum. When current is minimum, the voltage is maximum, right? So you can see if the circle is known as, if we start from here, so this is 180, then this is 360. So this is a phase change of a 90 degree, right? So this is one kind of representation. Let me take a water here. Now see the other conditions. So impedance, a vector quantity in the complex plane characterized by Z and theta. So if you represent Z, so we are saying like Z omega is not a real value, it is basically a complex. So it has real part as well as the complex part. So we can write Z is equals to Z dash plus Z double dash. So basically Z dash, this is the real component of impedance. Z double dash, this is basically Z double dash, and this is the complex component of the impedance. So maybe Z can be written as this Z, mod Z, as Z dash into Z double dash. Like this way can represent in the vector form, and in which both are having the angle of theta. So impedance as a vector quantity plotted in the complex plane. So the real Z dash omega and imaginary Z double dash omega, the component are projected on the x and y axis. The imaginary component is 90 degree out of phase, and Z can be written as Z dash plus Z double dash J, where mod of J can be calculated as under root of Z dash square plus Z double dash square. So by using this formula, we can calculate the mod impedance. Similarly, the angle of this theta can be calculated as tan theta is equals to Z double dash by Z dash. So these are the value how we can calculate the impedance in a system where we are having the AC signal or AC input. The impedance, or you can say the having two components, real and imaginary, right? So complex impedance is there. Now consider the cases, because we have the idea how impedance is going to behave, but what kind of circuit will be there in an electrochemical cell? So now we are going to talk about three things. Let's say one point, if there is only resistance, AC signal is there, but I am just considering, let's say only resistance is there. Second point, there is only capacitance. Third, maybe inductance. Second, maybe both two, resistance and capacitance, or these three together. Other cases could be there, capacitance and resistance could be parallel, could be in series. So different kind of cell may be formulated, and based on that cell design, we need to understand the basically the electronic circuit, whatever the typical circuit is there, and based on the typical circuit, we need to calculate the polarization resistance, or we can say the impedance value, and based on the impedance value, we can fit the circuit, and based on the fitting, we can calculate the again resistance, and based on the resistance, we can estimate the corrosion rate. So now see the first case. When we are having a corrosion cell, only resistance, right? So figure A you can see here. See the figure here, we have only resistance and we are applying a current. Current is passing through the resistance. So what is the voltage difference between point A and point B? So if this is the case, then we can see what is the relation between the current and voltage, whether they are in phase or there is any difference. So this is only resistance, nothing is going to be changed. When we are applying high current, we are going to get the high voltage. When we are applying a low current, we are going to get the low voltage. So basically both are synchronized. That is well understood, and in 10+2 physics, we already studied this kind of circuit. So maybe I would say, if you would like to know these things more detail, you just refer that discussion about the impedance in different circuits. So if you see here the vector diagram, so this is the axis of current. So this is also the axis of voltage. Therefore, I and V are represented here in the same direction, and where if you are measuring the voltage or the current at any time t, then you can just make an angle omega t. So basically this is with x-axis, this angle is omega t. So this is, if we are considering about this value, so this is the voltage. Similarly, this is the current. So in case of only resistance, both voltage as well as current are in phase, or you can say the value of theta is 0 and the impedance has no imaginary component, means it's only resistance, so there's no J value, only Z dash is there, Z double dash value is 0. See the case here, only resistance, so we can say, VAB means that the voltage difference between A and B, if you see in the previous figure, can be written as V cos omega, means the maximum value of voltage and which is changing with respect to the frequency and time. So the instantaneous current in the resistance can be written as I is equals to VAB by R, means just divide by the resistance. So you can calculate the value of I, or VAB is already known as V cos omega t, so it is divided by R. So maximum current amplitude is V by R. This is the maximum current amplitude, right? While the current as a function of angular velocity omega is defined as I is equals to I cos omega t. So again, So maximum value I, we can say V by R is capital I and then cos omega t. Now the second case, when we have only capacitor. So you can see again, now we are having a capacitor between point A and point B. We are applying a current I. So what will happen? Here we are going to see the charging and discharging effect, right? So maybe the value where we are applying the high current, it could not give the high voltage because it may be in the charging stage or maybe the discharging stage. So whatever we are observing, so this case is there. See here, the current is maximum, but voltage is minimum or something different. See this point, here the voltage is maximum, but current is almost close to minimum, right? It's minimum. So it's a difference. So we can say, let's say this is the minimum or the zero. So when voltage is high, the current is zero. When current is high, or you can see this point, voltage is zero. So there is a difference in the phase between voltage and current. And the current vector is ahead of the voltage vector by a quarter angle 90 degree. Means when the current is maximum, voltage is zero. The current is ahead or voltage is lagging behind. So it can be defined as, let's say this is the voltage, this one. So current is already ahead of the 90 degrees. So current should be represented like this way. This is the I. And it just representing with respect to omega t change. So here impedance can be written as Xc is equals to 1 upon omega c. So omega is the frequency and the c is the capacitance value, capacitor value. Or can be also written as, then current I will be voltage divided by the resistance. So here in this case, current will be equal to V upon Xc. Now the third case, when we are having the only inductor between the terminal A and B. So inductor formula, it's well known. If you say the change in the current with respect to time multiplied by inductor is equivalent to the voltage. Circuit can be like this, and in this case basically current is behind the voltage. Means see the voltage is maximum but current is here, it's zero. Current is max, voltage is maximum. So current is behind, or you can say the voltage is ahead with the 90 degree. In this case, voltage lead the current by 90. And we can represent I is equals to V by XL if XL is the impedance of the inductor. Now see the case, if all three are together, right? Because this could be a situation in our electrochemical cell when we are trying to analyze the corrosion by impedance spectroscopy. So impedance of the resistance, inductance and capacitance circuit, which where all these three values or these three components R, L and C are in series. So you can see again the figure A here, A and point B are there. In between we have the resistance, then in series inductance and then in series resistance. So this is the case. Then if you remember, if you just think about the value of theta, so in the first case it is 0. In this case this is 90 degree, right? So if you remember, current is ahead, sorry, here the current is lagging. In case of C, the current is ahead of the voltage. If you club all these three together, because all these are in the circuit, then how the vector diagram look like, that you can see in figure B. So now I am assuming the current is in one direction because there is change in the voltage. We are just applying a fixed current, there will be change in the voltage, right? We are using the voltage. So if there is a resistance, the resistance will be in the same direction, right? So the voltage due to the resistance, I can say the voltage difference across the terminal A and B due to the resistance. Let's say the resistance only. Then it can be written as VR is equals to IR, and it can be represented within the same line. But we also have the capacitance. So in case of capacitance, if you remember, current was ahead of the voltage, or we can say voltage is behind or lagging. So voltage should be 90° behind. So therefore we are representing this is voltage is 90° behind. So VC voltage and that voltage difference due to the capacitance across the terminal A and B will be written as VC is equals to IXC, and X is the impedance of the circuit. Now see the third component. The third component is your inductor. So in inductance case, your voltage is ahead of the current with the 90°. So see here, this is the inductance voltage which is ahead of the current with the 90°, and if I current flow through the inductor, then voltage will be VL is equals to IXL. Okay, done. Now what we are trying to find out, what is the overall voltage, right? Because we are getting the only one voltage difference, not the differences. So we have considered resistance, we considered inductance, we considered the capacitance, and based on these three, how this together is going to be having a circuit. So see, whatever the voltage is due to the capacitance and inductance, both are opposite to each other. So the difference between these two will be the overall value of the resistance and capacitance voltage. So you can say VL minus VC is equals to IX, and this is 1, this is, so now you have one value here and other value is VR. So now VL minus VC is one vector and VR is the other vector. So what is the overall of these two? Now there are two vectors which are perpendicular to each other. One value is VR and other value is VL minus VC. So how we can calculate? So this is equivalent to this. You just draw the normal of these two, and then whatever value is, maximum value is there, that is basically the sum or overall of these two components. We can say in this circuit basically V is equivalent to the IZ, where Z is the overall impedance of the circuit, right? So the voltage phasor is the sum of the phasor of the individual voltages, the maximum voltage V and the instantaneous voltage V. So corrosion cell impedance of the LRC series circuit, we already know VR, VL and VC, three are there. So we can just say the value of V will be mod of VR square plus in bracket the value of other voltage, that was VL minus VC square. We just substitute these terms, we can get the overall impedance value this much. But again, V by I is defined as the impedance of the circuit Z. So phasor VL is defined as the VL is equals to IXL. So similarly we can write it. The voltage amplitude across a capacitor is defined as Z, and Z value will be equal to this value, right? So if we have a LRC series circuit, then we can say our overall this, what we say, this impedance will be written as root of R square plus XL minus XC the whole square, or we can say R square plus X square. So X square is basically difference of these two, and then I is equals to V by Z. Again, XL we know can be written as omega L, XC can be written as 1 upon omega C. If you replace this value, you can get further value of Z. The value of phase angle theta of the source value V can be estimated by the formula tan theta, you already know, Z double dash by Z dash. So VL minus VC component is the imaginary component and VR is the real component. So basically by using this value you can say X by R. We can just get the value of theta, and the source voltage we can say it is in form of cos V is equals to V cos omega. That's well known. The current lag the voltage by angle theta between 0 and 90 represented by I is equals to I cos omega minus theta. So that I already explained in the previous figure. So if you are having these two values, so what we are going to get? If we have this value, we are going. So if we have calculated these things, so now we are going to get two important values, that is Z dash, the real value of impedance, and Z double dash, the imaginary value of impedance. So you have now total Z is equals to Z dash plus Z double dash J. Now think, if we plot these Z dash and Z double dash values in complex plane as we discussed a couple of slides back, which if we plot this Z versus Z dash, we get a very good plot, and that plot is very well known, and the name is Nyquist plot. This is well known in case of EIS spectroscopy, which can be used to evaluate the corrosion potential of metal and coating. So the overall idea is, if we do the impedance spectroscopic analysis by using potentiostat, if we can get the value of Z dash and Z double dash, if we plot this value in complex plane, we can get the Nyquist plot, and using Nyquist plot we can calculate the value of different resistance and the capacitance by applying the exact circuit. So we already know like what kind of circuit is possible in electrochemical cell, and based on that analysis we can get the value of corrosion potential, the corrosion resistance or polarization resistance. Then based on that value we can calculate the corrosion rate. So what is the AC impedance plot we are going to get? We are having the value of real impedance, we are having the value of imaginary impedance, we are having the value of total impedance. We also know that Z dash and Z double dash, we can also calculate the phase shift. So these values are there if only resistance, only capacitance, or if we are having, let's say, only RNC circuit. So these are different variety of circuit is possible, or we are having R and C circuit in parallel also. So we just talk about the series, but you can calculate the values if you just consider if these are in parallel. So let's say I'm just giving the hint or only couple of ideas like how we can plot Z and Z double dash, or how the Nyquist plot look like. So see the case 1, the case A. Let's say we have only the resistance in the circuit. So the value of Z double dash will be 0. And if you plot, Z is equals to R resistance plus 0J, because Z double dash is 0. So you are going to get a fixed value. So that is, therefore they are representing only a single dot, means the value of resistance. Whatever the value of Z double dash, that is equivalent to the value of resistance directly. See the case B. You have only capacitor in the circuit. So your real part is 0. So Z is equals to 0 minus J omega C. So therefore, if you see the plot, if you change the omega based upon change in the frequency, there will be difference in the value of Z double dash, but the value of Z dash is 0. So therefore we are getting all the point plotted in a single line here. See the third case, when we are having a resistance and the capacitance, and both are in series. So what will happen? In case of series, the value of R is fixed, and then when you are changing the omega, there will be change in the value of the basically your imaginary component, gel double dash. So therefore, if you see the plot here, all dots are here. So it shows this is the value of real component, basically the resistance, and then this plot shows there is a variation in the Z double dash value with respect to change in the frequency or the variation in the omega. So if this is the plot is there in Nyquist, we can understand there is a two component in the system, right? So by just looking the Nyquist plot, we can have the idea what kind of components are in the circuit, and then based on that analysis we can fit the circuit and we can get the value of resistance. Now see the fourth case, the case B, where we have the resistance and the capacitance in parallel. That is interesting, and this is more common case, and most of the electrochemical cell we are going to get this kind of nature, where our resistance and the capacitance are in parallel. We will explain later maybe. You just see the electrolyte interface, we are having one capacitance, and then another capacitance which is in the resistance, electrode material which is in the parallel of the circuit. So that's why your capacitor, the resistance is parallel in an electrochemical interface. So if you see here, if this is the case, then we are going to get difference with respect to change in the frequency. There is a change in the resistance. So this is shows basically the overall resistance. This is the resistance at the beginning, and this is the resistance at the end, and it looks like a semicircle. So if your Nyquist plot form a semicircle, then we can say there is basically the resistance and the capacitance in parallel. Now see the other condition. Let's say you have resistance and the capacitance series, and in first here and then this. So what will be the complex plane plot or the Nyquist plot? So if these two circuits are together, then these two things will be clubbed out. Means at the beginning you will get a straight line and then you are going to get a circuit, or the reverse way. Let's say if some resistance is there or another some capacitance are there, so then maybe half circle, then a straight line, or a straight line with some angle. So these all different nature shows what different kind of circuit elements are there and how they are connected to each other, the parallel, the series, or the mix of these. So that understanding is need to be understand if we are going to analyze the electrochemical impedance spectroscopic data. See this AC impedance plot. So this is the common plot in case of our electrochemical cell, where we are going to have R omega. R omega is the resistance of the electrolyte, or you can say the overall cell. Then we are having an interface. So in interface we are going to have a capacitance behavior. So capacitance, at the same time if there is a polarization, then we are going to have the polarization resistance or the resistance of the circuit. So these three elements are there: the ohmic resistance, the polarization resistance defined as the resistance at the electrode or solution interface, the capacitance, right? So the Nyquist plot is also, so if this circuit is there, then our plot could be different. And this, if you plot this Z dash, known as Nyquist plot, sometimes also called as complex impedance plane diagram or pole plot. For each frequency, the imaginary component Z double dash is this format is plotted versus the real component. So if we plot this Z versus Z dash, then we can evaluate the value of polarization resistance Rp, and then we can calculate the corrosion rate. So by using this method, we can do the analysis. Let's see one example. So if you have the similar identical circuit, whatever I have shown in previous slide, so if you plot the Nyquist, it will look like something this. Means something this line, that we are going to make a half circle. So basically our circle will not start from 0. It will start with some value of real impedance, then it forms a semicircle. And if this is the case, then how this is the case we are going to observe when we are plotting the Z dash versus Z double dash. So how we are going to analyze the parameter? So first of all, see at the beginning you are having a very high frequency. At the end, this point, we are having a low frequency. Low frequency. And here basically we are having a high frequency. So at high frequency, the imaginary component Z dash is 0. When the condition, because here at high frequencies, basically the high frequency start from here and slowly goes down, and we are measuring this plane. So the value at high frequency side, when Z value is 0, we say the Z dash is equal to the ohmic resistance. So basically this value you can easily calculate, and this value is equivalent to R omega. Similarly, at very low frequency, so this is the least one or the low frequency. Here also this is a point, another point where the Z double dash component is 0. And at this value, we call this is the overall resistance. Basically, this is the sum of Faradic resistance or polarization resistance plus ohmic resistance. So, if you see from here to here, if you are able to see my cursor from the origin to this value, first point, this is R omega, then from R omega to this value, this is Rp. So, if you know this point, we can easily calculate the value of Rp by just substituting the value of R omega. So ohmic resistance R omega is same at all frequencies. Basically with frequency dependent, whatever you change, but R omega will be same. So Rp can be calculated. So these were the one. Similarly, if you remember, we have Z dash. So we can get the mod of Z. We also aware about the frequency applied during the measurement. We also have the value of theta. So there is another plot, it's well famous, known as the Bode plot. In Bode plot, what we plot, that is the mod of Z dash. So with respect to change in the frequency, okay, how the mod of Z and how the theta is going to vary. So see here, in the x-axis we have the frequency log omega, and in y-axis we are having mod Z as well as theta. So if we plot, the plot will look like something this solid line. This is the solid line plot for this one, basically mod Z versus frequency log. And if you plot theta versus this, then it will look like this way, this dotted line, right? So if this is the things, the value where we are having this one, so you can just put here the line, we can get the value of R omega, and similarly the upper cutoff is equivalent to the Rp plus R omega. So the simple thing, if we just plot frequency log omega versus mod Z, both values are known for the system, we can also get the value of R omega and Rp plus R omega. So easily we can calculate the value of Rp here again. Value of Z, value of tan, Rp R omega. So what I have discussed till, if we do the electrochemical impedance spectroscopy, we are going to measure the Z dash and Z double dash. we can either plot Z and Z double dash in a complex plane or we can, so that is known as the Nyquist plot, or we can also plot the double dash or basically the mod of Z with change in the frequency, and that is known as the Bode plot, and using both the plots we can calculate the value of RP, and based on this value we can estimate the corrosion rate. Here one example is there, just to get the idea. The Nyquist response, basically the Nyquist plot is there for electrode which is having the different kind of coating. The coating material are zinc, nickel, cadmium, or zinc, nickel, copper, nickel, zinc, or nickel, zinc, or these kind of combinations of coatings are there. So which coating is better, right? So the coating which is having slow corrosion rate can be considered as better. So that can be easily analyzed by just impedance spectroscopy, and data look like this. So if you see, so this is the real data. Nyquist plot obtained from various coating in 0.5 mole Na2SO4 plus 0.5 mS3BO3 solution at pH 7 solution. So see, in x-axis the real Z value omega varying from 0 to 2500, and in the y-axis the imaginary Z double dash omega. Sometimes people also write Z and Z dash, so don't be confused. X-axis is the real Z and y-axis is the imaginary. Here they have just Z and Z double dash. It's even good, now we have clarified this point. So it's again 0 to 900. So see the plot. In case of zinc, very small circuit, but even not even the circle half. Then zinc, nickel, then cadmium, then zinc, nickel, copper, then electroless coating, then nano coating. So these all are having different height. So even the value of real is different. Similarly, the value of imaginary is different. But see the important point, all values are starting from the same thing. Why? Because the solution resistance or the value of R omega is same, because this is the point from which we can calculate the value of R omega. But see the end point. See the value of R omega plus RP, that is very different in all the cases. So the resistance are very high in this case, polarization resistance is very high in this case, very high in this case. Slowly it's less here. So even in each sample we can get the value of RP here, right? And by using that value of RP we can calculate the corrosion rate. So the solution resistance remains the same for all the frequency. Now fit a simple equivalent circuit as we discussed earlier, consisting of ohmic resistance, double layer capacitance and polarization resistance. We can get these values, and whatever the outcome was reported, like the electrode deposited nickel zinc alloy and electroless nickel zinc and phosphate offer a barrier resistance in the order of 200 ohm, which is 5 times higher than the typical cadmium deposition. Right. So these are all about electrochemical impedance spectroscopy, and now I think after this I have discussed this electrochemical method to analyze the corrosion or to measure the corrosion rate. So today I will stop here. Thank you very much.